So we'll start with what explosion is, and then we will talk about the variable mass system. Whenever, let's say, an explosion occurs, there is no external force. Now think about this. There is a mass m, it breaks up into two fragments, not necessarily of equal mass. What happens is you burn the fuel, and therefore the propellant gases, they start ejecting, and therefore the rocket starts. So let's say there is a hose and water is being thrown out of that hose. So you have seen firefighters doing that. Hello students, welcome back in today's class. In today's class, we are going to talk about a very simple and short topic, that is about variable mass system. So far, whatever discussion we've had, we have talked about how the motion of an object changes when force is applied, but we always assume that the mass, the object remain intact. But in today's class, we are going to discuss that aspect where even the mass of a system can change. It can gain mass, it can lose mass. So think about it, maybe like an explosion or rocket propulsion, where you can assume that the mass of the system can also change. So that is something that we are going to explore, what is the physics behind that. But before we actually go into that, let's discuss the basic concept of an explosion, right? So we'll start with what explosion is, and then we will talk about the variable mass system. So this class is in continuation, where we are discussing various aspects about forces. So you should know the basics of force, that is what are the Newton's laws, what is the basic definition of force, momentum, all these things. Only then this class will make sense to you. Alright, so without wasting any time, let's get started. Let me give you the basic definition of explosion. In explosion, a mass breaks into smaller masses. Usually chemical energy gets converted into kinetic energy, which is called the Q value of the explosion. So we've learned that energy can never be created, nor it can be destroyed. So what happens here is that, let's say a bomb explodes. So whatever is the chemical energy stored inside the bomb, that gets converted into the kinetic energy of the fragments, isn't it? So you might see that energy is being created, kinetic energy has been gained by the fragments, but the internal chemical energy of the bomb has been utilized. Alright, so in that sense, mechanical energy is created or chemical energy is converted into mechanical energy. So whatever is the kinetic energy of the fragments, that basically gives you the Q value of the explosion or the reaction. Alright, so you can write this down. Then we take a simple example to understand how this is working. So before we take that example, I hope you understand the basics that whenever, let's say, an explosion occurs, there is no external force. Now think about this. Let's say an explosion occurs and this is a mass m, and it in a very simple fashion, let's assume that it breaks into two fragments. What is going to happen when this explosion occurs? You would say this will gain momentum, this will also gain momentum, but you should be very clear about one thing, that there is no external force. So whatever forces have been applied are internal. One fragment will apply on the other and the other fragment will apply on the first one. What does that mean? There is no external force. Therefore, if we follow up with Newton's second law, that is the force is the rate of change of momentum, then this value is equal to 0, means momentum remains conserved. There is no change in momentum, isn't it? That is why if I ask you to imagine this explosion to happen, and let's say it is breaking up in two fragments, you would always imagine if one fragment flies to the right, then the other needs to fly to the left. You cannot imagine all the fragments to fly off in one direction, isn't it? So that's because the momentum has to be conserved. So if one fragment takes the momentum forward, the other has to take it in the opposite direction. Alright, so now I hope you understand the basic physics of it, that momentum will always remain conserved, and therefore it is another application of the principle of conservation of momentum. Write this down, then let's take the example. Alright, so a body of mass m breaks apart at rest into two pieces of mass m by 4 and 3m by 4. So in fact, it's a very similar situation that we have just discussed. that there is a mass m, it breaks up into two fragments, not necessarily of equal mass. So let's say one of them is 3m by 4 and the other is m by 4. So let's say the velocity acquired by the lighter fragment is v1, then the heavier fragment will acquire a velocity v2. So just now we have discussed that final momentum will remain equal to the initial momentum, which was 0. Why? Because the bomb was at rest when it exploded. Alright, so m by 4 times v1 plus 3m by 4 times minus v2. So the value of v2 turns out to be v1 by 3. So we can say, of course, if the lighter fragment flies off with some velocity v, then the heavier fragment will fly off with a velocity v by 3 in order to acquire the same momentum. Think about recoil of gun. Even that is an example of explosion. That is why when you fire a bullet, when the bullet moves with some muzzle velocity, the gun has to recoil. But the velocity of the gun is in the backward direction is way too small because it is way heavier as compared to the bullet, isn't it? So firing of a bullet is another example of explosion. Alright, so overall kinetic energy created in the reaction in the explosion is Q. So we can write that this is going to be half m by 4 into v1 square plus half 3m by 4 into v2 square, isn't it? So that is the overall kinetic energy created. What is the question asking? It is asking the kinetic energy only carried by the lighter part. So it is asking about this term. So what we can do here is, let's multiply. In fact, let's write v2 in terms of v1. Let's do that. 3m by 4, and we can write v2 as v1 by 3, isn't it? Now, if you rewrite this, what are we getting? Half m by 4 times v1 square. Let's separate this term, and what are we left with? This is 1 and this is going to be 1 by 3, right? Isn't it? This is going to be 1 by 3. 1, 3 and 1, 3 will cancel out, and therefore it is going to be 1 by 3. Alright, so this Q is equals to half m by 4 times v1 square. So you don't see the solution. I hope you now know the protocol. You have to try the question yourself first and then look for the solution. Alright, and this is going to be 4 by 3. Now what is the kinetic energy of the lighter fragment? It is, of course, kinetic energy is equals to half m by 4 into v1 square. So we can replace this whole term with k, and therefore Q becomes equal to k times of 4 by 3. So what is the kinetic energy of the lighter fragment? The answer is going to be 3 by 4k Q, isn't it? What can you conclude? That even though the momentum taken by both the pieces is the same, but the kinetic energy taken by the lighter fragment is 3/4, that is 75% of the total energy. So this will take 75% of the energy, and the heavier one would take therefore 25% of the energy. This is a very simple example of explosion because we've just assumed that there are two fragments. Alright, copy this down, and I hope you understand now what explosion is and what is to be kept in mind, that we have to conserve momentum before and after. Even if the bomb was initially moving, then also you can apply the principle of conservation of momentum. Alright, so now let's talk about variable mass system. So think about this, rocket propulsion. So what happens is you burn the fuel, and therefore the propellant gases, they start ejecting, and therefore the rocket starts losing mass. But because it is losing mass, the gases are going in the backward direction, giving a reaction to the rocket in the forward direction. Why is it necessary? That's because rocket has to fly, it has to go into the interstellar space. There's no atmosphere, there's nothing to take reaction, and I hope you know that to move forward you need to have a reaction. Someone needs to apply an external force on you. So how is the rocket mechanism working? It is relying on the reaction or the thrust force obtained by ejection of the gases in the opposite direction, isn't it? So now let's quickly rearrange what we have learned so far. So you do understand that momentum is equals to mass into velocity, right? But today we are going to write it in a different fashion. Let's say if mass changes, and also the velocity. So let's put it like that, and also the velocity. So for the rocket, we can say that the mass is changing, the velocity is changing. So if let's say initial momentum was mass into velocity, that is mv, the final momentum is, let's say, m plus delta m into v plus delta v. I hope you understand what I have done here. I have written it as m plus delta m, v plus delta v. So delta m represents the change in mass, delta v represents the change in velocity. So delta p now, that is p final minus p initial, that's going to be m plus delta m into v plus delta v, and subtract mv from that. Alright, so that's delta p. What if I just have to write the force in this case? So you would say divided by delta t, isn't it? So that's going to be delta p by delta t. So let's divide it here. Alright, so the force is going to be, now think about these terms. So you will have 4 terms here, mv plus m delta v plus v delta m plus delta m delta v, isn't it? Minus mv. So this term and this term will cancel out. We can afford to ignore this term. Why? Because normally the change in mass is going to be small. At an instant, change in velocity is going to be small. So these two small quantities, when being multiplied, will make this term way smaller as compared to the other terms. So that is why this cancels out. We are ignoring this. So today we are having another way of looking at force. What is that? So we can write this as m delta v by delta t plus v delta m by delta t. That is more prominent, like this is more precise how to write force. So in the previous classes, what we have been doing was, we just wrote F is equals to delta P by delta T, and then we wrote momentum is simply mass into velocity, and since we always assume that mass does not change, and therefore we wrote F is equals to m delta V by delta T, and that delta V by delta T was written as acceleration. But today we have obtained a more precise, a more detailed expression of Newton's second law, that this is the correct way of writing Newton's second law, that F is equals to m delta V by delta T plus V delta m by delta T. So we accommodate the scope that if mass also changes, then this is more relevant equation. But if the external force is 0, then this term becomes 0. That is the case in a rocket. What happens in a rocket? So when the gases eject, we can write, let's say they are ejecting with a speed v. So the net external force is 0. There is no external force. It is the rocket just obtaining the reaction of the gases. So if we take both as system, then there is no external force. So we can write that m delta v by delta t for the rocket is equals to v delta m by delta t. Now think about what is delta m by delta t. So delta m by delta t gives you the rate at which the mass is being lost, isn't it? So we can write the acceleration, that is delta v by delta t, is nothing but, if we write delta v by delta t, it's going to be minus v by m times delta m by delta t. Think about why this minus sign. That's simply because with time, velocity is increasing for the rocket, but the mass is decreasing. So if there is a positive change in velocity, but there is a negative change in mass, so this delta m is always negative, and this negative becomes positive. So keep in mind, the rocket is not gaining mass, here it is losing mass. If something gains mass, then it has to lose velocity. Think about an open cart traveling in rain, moving on a road in rain, and you just push it and let it go. Imagine rain dropping inside the cart. As the mass would be increasing, the cart would be slowing down. So if the mass increases, velocity decreases. If the mass decreases, velocity increases. So keep in mind this equation. This is the governing equation here, that acceleration is equals to minus v by m delta m by delta t, or force is equals to minus v delta m by delta t. That is the force the rocket will experience on ejecting the gases in the backward direction. Let's do a problem to understand this, but you first process all this, pause the video, think about it, lot to learn, then we take an example. Alright, so now let's talk about a small firework rocket has a mass of 65 gram. The initial rate at which hot gas is lost from the firework after it has been lit is 3.5 gram per second, and the speed of release of this gas from the rear of the rocket is 130 meter per second. That's quite huge. Calculate the initial acceleration. So just now we have learned that acceleration is equals to minus v by m delta v by delta t. All right, so I have shown that to you again, delta m by delta t. That is how you govern the acceleration of the rocket when it is going to move forward. So the velocity with which the gases are being ejected is 130. The mass of the rocket is 65 into 10 raised to the power minus 3. I've converted gram to kilogram. Now delta m by delta t, at what rate the rocket is losing mass? That's 3.5 gram every second. So that's going to be 3.5 times 10 raised to the power minus 3 divided by 1. Why 1? Because already the data is given to us in per second. What if they would have given this in per minute? Then we would have divided it by 60 to convert it into second. As you do understand that time has to be substituted in second in case of SI system. So this factor and this factor cancels out. 65 times 2 is 130. So the acceleration is going to be 7.5, 3.5 into 2, that is 7 meter per second square. Now you would say, why not minus sign? So put a minus here in fact, because delta m by delta t is going to be not 3.5 but minus 3.5, because the rocket is not gaining 3.5 gram every second. In fact, it is losing that. So this minus and this minus will become positive, and this is going to be 7 meter per second square. All right. So I hope you have understood how to apply the concept in case of variable mass system. Let's take another example now. All right. Water exits a horizontal pipe at a rate of 40 kilogram per minute with a speed of, what is the horizontal force? What horizontal force is needed to keep the pipe in place? Now think about another example. So let's say there is a hose and water is being thrown out of that hose. So you have seen firefighters doing that, and it's not easy to hold on to the pipe. In fact, you need 2 or more people to hold on to the pipe. That's because when the water is gushing out of the pipe, you get a reaction, isn't it? It's just like rocket, how the gases eject and the rocket gets a forward push. Just like that, it's like a recoil. When the water is gushing out, the firefighter gets a recoil, and therefore to hold on to it, you need more force, you need more stability, and that's why multiple people hold on to that hose. Or you can take an example. Let's say you leave a pipe in the garden and you turn on the tap. What's going to happen? When the water is going to gush out, the pipe is going to move by itself, again indicating that there is a reaction force that the pipe is experiencing. We are talking about that here. We've just learned that force external was equals to m delta v by delta t plus v delta m by delta t. And if this external force is 0, then m delta v by delta t for the pipe, the force experienced by the pipe, that is equals to v delta m by delta t. This we can call as the thrust force. We can call this as the thrust force. So this is the force the firefighters do experience, and therefore it is proportional to velocity, shouldn't it be? So more the speed with which the water is gushing out, more is the recoil force. At the same time, it is proportional to the rate at which the mass is being ejected out. All right, so if we do that, let's do this calculation. The mass is 40 kilogram per minute and the velocity is 9 meter per second. So 40, as I was just pointing out, if it is per minute, you have to convert that to per second. So let's divide it by 60. So what are we going to get? In fact, we can do this calculation. this is 2 times, this is 3 times, and this is then 3 times. So the answer is going to be 6 Newton, isn't it? This is the force that the pipe would experience, and therefore you will need to apply this force if you want to keep the pipe stationary. Easy, right? Let's do the next one. All right, let's take another interesting example. A mass of 0.48 kilogram of water leaves a garden hose every second. The nozzle of the hose has a cross-section area of 8.4 into 10 raised to the power minus 5. The water flows in the hose at a speed of 0.71 meter per second. The density of water is 1000. Calculate the speed at which the water leaves the hose. All right, so I hope you can imagine, let's say this is a hose and it narrows down into a nozzle somewhat like this. All right, so what happens here is that when it is flowing through the hose, it has a broader cross section area, but when it narrows down, the area decreases, and to accommodate the same amount of water, the velocity should increase. Think about this. You are, let's say, using a hose in a garden, and when you narrow down the opening of the pipe, you always see the water gushing out with a greater speed, isn't it? So if the area reduces, the velocity has to increase because the same amount of water has to flow out. So let's say if the velocity of water here is u, and it will become v here, isn't it? So first let's figure out what is the velocity with which the water is leaving the hose. So for that, let's understand that mass is equals to density into volume. I am writing this for the water that is leaving the nozzle. So the mass is, let's say, 0.48, or we can also keep it like that and divide by T on both sides. So when we divide by T on both sides, what are we going to get? So this is going to be the mass leaving per unit time, and the volume can be written as area into x. Why so? Because when the water is flowing through the pipe, you can take it as a cylindrical shape. So volume can be written as cross section area times x and divided by time. So the distance divided by time is going to give you the velocity. So the mass leaving is going to be rho a v, isn't it? Where v is the velocity with which the mass is leaving. So we can write this as delta m by delta t. Why do we need this? Because just now we have learned that force is equals to v delta m by delta t. Now what is the v value here? That is the velocity relative to the hose that the water is leaving, isn't it? So think about that. This force is going to be the relative velocity, that is going to be v minus u into delta m by delta t, that is going to be rho a v. Right, so we have discussed the physics of how a hose works. So here the water is moving through the hose, it narrows down, it leaves with a greater speed. Definitely yes. So v is greater than u here, because if the area reduces, the velocity has to increase, and the force that the hose is going to experience in the backward direction that we are going to experience is equal to v minus u times rho a v. So this is what they are asking. First they are asking us the value of v with which the water is leaving the nozzle. So for that, let's use this. The delta m by delta t value is given to us very easily, 0.48. The density is 1000. Area of cross section is 8.4 into 10 raised to the power minus 5. And then v is what we have to calculate, isn't it? So let's do this calculation. This becomes 48 divided by 8.4. And this is giving us v is equals to 5.71 meter per second. All right. So this is the velocity with which the water is leaving the nozzle. And if we use this formula, that force is equals to v relative, which is v minus u times delta m by delta t. Why? Because straight away we know the rate at which the mass is going out, and therefore v minus u becomes 5.71 minus 0.71. So the velocity of the water while moving through the hose is 0.71. So let's subtract that, and delta m by delta t is 0.48. So this becomes 5. 5 times 0.48. Let's do that calculation. So this is turning out to be 2.4. All right, 2.4 Newton. So that again an example of variable mass system. Let's take another example and finish off today's class. Alright, so now let's take this question. A spacecraft is initially at rest in outer space. The spacecraft is propelled by a rocket engine that ejects exhaust products at a constant rate of 2.8 kilogram per second. So per second 2.8 kilogram of propellant gases are being ejected with a speed of huge speed 3.6 into 10 to the power 3 meter per second relative to the spacecraft. The initial mass of the spacecraft and its fuel is 4 into 10 to the power 4 kilogram. Calculate the thrust force. So one thing to be noted here is that it is already in the outer space, because if it would have been on the ground, then the force of gravity should also be taken into account in the free body diagram, but that is not the case here. So calculate the thrust force of the rocket engine. So F is equals to, we have just learned that the relative velocity times delta m by delta t. So velocity is given to be 3.6 into 10 to the power 3 and delta m by delta t is 0.8. When we multiply 3.6 and 2.8, approximately we are going to get 10. 10 times 10 to the power 3, it's going to be 10 raised to the power 4 Newton. That is the force, right? With this force, we have to also calculate the initial acceleration. So I think it's easy now because we know the force. Now let's equate this force to mass times acceleration. So force is 10 raised to the power 4 and mass is 4 into 10 raised to the power 4. So mind you, the mass is ever changing. So this value of acceleration is only valid when the rocket is initially when the rocket has fired this much gas, because as the gases are being ejected out, the mass of the rocket is continuously decreasing and therefore the acceleration is also changing. But at this particular instant, the acceleration is going to be 1 by 4 and that is going to be 0.25 meter per second square. So this is an acceleration that we can manage with because already the rocket is in the outer space, but you would need much more force when you are at the time of liftoff, right? Because there the force of gravity is also acting and therefore you need to counter that as well. So I hope you are able to get the basics of how variable mass system works, and now we have accommodated that component also. Very soon we are going to start with the previous year questions, and that is where we will apply everything that we have learned so far. Alright, so that's all for this particular video. I hope you are enjoying learning with us. But that's all. See you next time. Bye bye. If you enjoyed this video, please don't forget to like, share and subscribe to our channel.